and he also works on the computational material sciences. So presently he is a director of ISI Kolkata. Before that, he was a institute chair professor at IIT Bombay till 2017, and before that he was till 2015 he was director of CSIR lab NCL Pune, and he was also once additional director charge of another CSIR laboratory CSMCRI Bhavnagar, Gujarat. Before that, he was a head of the physical and material chemistry division of CSIR lab NCL Pune. So among various awards, 2000 he got the Santishwar Bhatnagar Award. Then 2008 he got the J.C. Bose National Fellowship Award. And 2014 from CSIR he got the Shastra CNR Rao Award in Chemistry and Material Sciences. 2003 he became the Fellow of the Indian National Science Academy. 1998 he was the Fellow of the National Academy of Science, and 1996 he became the Fellow of the Indian Academy of Science. Other than that, he has a huge number of publications, and he has a various editorial board and huge number of students. So with this brief introduction, I'll request Professor Carl to start his talk.
Thank you.
Okay, sir. Okay, sir.
Thank you, Raj, for inviting, first of all, CRSI Northeast Chapter, Dr. Parameswar Iyer, and others, for inviting me to this. Am I audible?
Yes, sir.
Yeah. So, to invite me to give this talk, let me try to share my presentation. So let's see. Is it seen now? Can you see the presentation? No?
You can. There is a share button, sir.
Yeah, I've gone to the share button only. So there is a share tray, right? More action. Let me see. There is a share button. Is it from the more action?
In the top, there is a upload button. Is there symbol? In the top, before the just after the mic video symbol, there is a share button, sir.
There is an open share tray. Is it the same one?
From there you have to select that what you want to share, sir. That if you like your PPT or your screen.
Yeah, that's what I'm doing. Is it seen now?
No, it is showing your account, sir. So you can share from the share tray. You can share the PPT you want to share.
I have gone to the PPT. I've opened the PPT, but I don't know why it is not coming. What is shared window? This is the problem. Stop sharing. I'm trying again. See, I'm getting an open share tray, right?
Yes.
In my open share tray. After that, what do we have to do? I am getting all the documents.
Yeah. Now
I'm choosing my
PPT. You can choose your PPT.
Yeah. Are you getting now?
Yes, sir.
Okay, fine.
Now it's fine. Now we can go to the full screen mode. It will be fine.
Yeah. Is it okay?
Yeah.
Is it moving? Yeah. Okay. All right. All right. Thank you for inviting me for this talk. And this is, of course, a very pleasant duty because it's also the National Chemistry Week. And the celebration of chemistry is being done by several CRSI local chapters. In fact, I'm very happy to see that the CRSI itself is doing in a very big way, particularly this year. And I must thank the CRSI President, Professor Vinod Singh, for energizing the local chapters. And I know several local chapters. In fact, that's why I'm very busy, because several local chapters are organizing different types of meetings, which I am kind of attending. Am I audible?
Yes, sir. Yes.
Yeah. So I am going to speak today in the next 40 minutes on the computational chemistry from molecules to materials. So I'll just quickly show what the computational chemistry can do. I have been in these 3 cities that was mentioned in Pune, Mumbai, and Kolkata. This is Pune, this is Mumbai, this is Kolkata. And each of the 3 cities, some of the work that I'm going to present has been done in different cities. Of course, I just want to tell very quickly about the ICERs. It's a research and innovation university. You have ICER Kolkata, which came along with ICER Pune in 2006, and then we have Mohali, Bhopal, and Trivandrum came at the same time in 2008. Tirupati and Berhampur came 2015 and 16. This is, of course, our campus. It's quite a green campus. We have a natural lake inside the campus, as you can see. And our first phase of construction is now over. And we hopefully want to build more buildings. And of course, we have a student strength of about 1,500 currently, out of which about 1,000 are BSMS and about 500 are PhD students in different disciplines. We have 5 disciplines of biology, chemistry, art science, physics, and mathematics, in which we give degree. But we also have now opened up humanities and computer science as an additional departments, which will administer courses for BSMS as well as do PhD degree. So I think that is the current status in which we are working. We hope, of course, to add more departments, more number of students in near future. So we are about 14 years old, and the total land is about 201 acres in the campus. We have been consistently ranked high. In the 2020 NIRF ranking, overall is 29. We have also very high Nature Index ranking, particularly among the institutions which came around this time that ICER Kolkata was born. So of course, comparison with the old IITs and are not very relevant at this point, but certainly compared to the IITs which came up at the same time, we are doing pretty well. I just wanted to quickly say about the chemistry education that today it is very important because since we are doing education, is very, very important that we.
Sir, sorry, sir, your slides are not moving actually.
That's what I was telling you. So let me see. Many times it happens that way. Is it now moving? Hello, is it moving now?
Yes, now it is in the second slide, sir. Yes, yeah, now it's fine.
See, as soon as I go to the full slide, sometimes there's a problem. I faced it in Teams before. I don't know. Is it okay? I can continue like this.
But it is not full slide, sir. It is not in the full slide mode.
That is what I'm saying. Once you go to the full slide, it does not move many times. So like, for example, now is it moving?
But it is not in the full mode.
It's still not in the full mode.
No,
so is it not possible? Is it possible to go in this mode itself without going to the full mode?
Yes, sir. Yes, sir. It is okay.
I don't know what is the problem with the full mode. It will take time to correct it. I think this is, you can view it. There is no problem.
Okay, sir.
So you have the, whenever there is a smaller thing, I can go to the full mode, no problem. So you have the chemistry education, and that's very important that we should talk of the hierarchy of chemistry education, because we are in an institution where integration of research with education is very, very important. Of course, we are now all facing the challenges of teaching and doing research because of COVID-19. So the online learning, how do you do online research? How do you do experimental research? There's so many things that all the institutions are grappling. I will not mention too much about it, but I just thought I'll flag that today we are at a crossroad. Science, of course, is very important that all of us understand. And science provides several opportunities for research, in academia, as well as industry. And then you have lots of alternative science careers. But more importantly, when I took up science, I must say I took up not because of any career, but because it could fulfill mine. We never thought, those days, many students did not even think of jobs and all that. You just did something, and because we are happy to do science. I think that's very important to realize. So as I said, there are lots of opportunities for the young people to do science. And we tell that in the ICER, you can get jobs in academic institution, research laboratories, mission-driven projects, industry, as well as one can become entrepreneur. In fact, Dr. Pradeep, who will be giving talk after me, is a brilliant example of a scientist turned entrepreneur who has spun off companies. I think it's very important for many students to learn that we have to not only look for jobs, many of us have to look for jobs, of course, but there should be many who should be able to create jobs. And I think that's very important. So there are lots of opportunities for research. But what is important in the startup as far as science, that we must go to the deep innovations. Deep innovations are basically high-tech scientific innovations. Fundamental science obviously cannot be predicted. It comes out of necessity. Sometimes it comes out of accident. Sometimes it comes out of curiosity. Sometimes even in dreams. Research, the thoughts come in dreams. So there are several examples, like for the necessity of Archimedes, accidental discovery, discovery of urea, for example, is an accidental discovery. Then curiosity, of course, very famously, Isaac Newton, who looked at apple falling. And of course, Kekulé had dreams that the snake seizes its tail and then discovered the structure of benzene. So I think there are several interesting things that happen. What is very important is to understand the structure. I want to go full mode in this particular thing. Can you see it full mode? Or you can't see at all?
No, here it is fine, sir. No problem. You can see it.
Yeah.
Also.
So for example, we go to a quadrant of Bohr quadrant, which is high basic research, low use, or a Pasteur quadrant or high. This is high applied research, low quest for fundamental understanding. What is important is that when we start, we are actually in this quadrant, and we must go up to this quadrant. So basically, the tendency of the educator should be to bring students up to the Pasteur quadrant, where there will be high fundamental science and a high basics understanding. Is this seen now? Has the slide changed or no?
Yes, sir. Yes, sir. It is fine.
Okay. So we have the Nobel laureates from Indian and Indian origin. I have put all of them together. There are science Nobel laureates, of course, Sir C.V. Raman, Chandrasekhar, Hargobind Khurana, Venki Ramakrishnan. In this order, of course, C.V. Raman, Hargobind Khurana, Chandrasekhar, and Venki Ramakrishnan. We have to understand how to have more Nobel laureates. How do you create value in science? And that is very important. One of the things that is happening is, of course, please tell me the slides are not moving. I have moved the slides. Is, of course, a hierarchy of sciences. When we talk of chemistry, physics.
So it is not moving, sir. Again.
I know that whenever I'm going to the. Now coming.
No. Yeah, now it's fine. So this is fine. This is fine.
So I think we have to keep why it is happening, because I could not come a little bit ahead of time.
No, sir, this is happening. So you can go in this mode.
Yeah. So there is, when we always believe the starting of chemistry is very difficult, there is the instinct in chemistry. That is why I feel at the school level, children are interested in physics and biology. Biology is something that you feel. But chemistry happens by transfer of knowledge. Transfer of knowledge, whatever is experience, can't feel it in their own. So many times in this transfer of knowledge, evidence of the learner makes sense of teaching and alternative concepts of the materials presented to them. Teaching of chemistry very difficult. Physics you see every day. Apple falling and so on. You can see plants, animals. They are subjects which are very easy to feel. And then a hierarchy of subjects, a hierarchy of science built upon each other. Conventional way of thinking that the physics is built on mathematics, chemistry is built on physics, biology and chemistry, psychology and biology. I know this is not wholly true. There is consistency. And today maths is not just for physics, but for chemistry and even biology. Data science has revolutionizing biology. So I think there are large part of biology also that make direct or indirect applications of chemistry. So it's very hard to say the hierarchy of sciences. The hierarchy of sciences that we are built, we are fed in our childhood has almost vanished. So what is required is an interdisciplinary thinking, and particularly with the material science that has happened. Interdiscipline is also very important in all the challenges, future challenges that we are going to solve, in particular, on the renewable energy, sustainable resources, energy efficient processes, environment friendly processes, which is green chemistry, affordable healthcare, cultivation of farms, technologically enabled defense system. Many of these are the future challenges of the country, and they would all require interdisciplinary expertise. Although chemistry will remain at the center, because chemistry is a very central science, so it's very important to realize that the chemistry will always be there. In terms of renewable energy, I think that is very, very important from the sustainable sources, where chemistry plays a very important role. We have, for example, solar energy, sunlight storage, wind energy, fuel cell, bio-waste to alcohols and fuel, hydrogen energy, nuclear energy, CO2 into fuel. Many of these are investigated very strongly by the chemists. In fact, hydrogen energy is very, very important in fuel cell. Then carbon dioxide into fuel is a very big problem. Reduction of CO2 to methanol, formic acid, and even people are dreaming for methane. Of course, solar energy to power, thermal solar energy is already there, conversion to heat, but electricity has become, is a big challenge still. Of course, the challenge is really to make it affordable. That's a very important thing. So many of these, chemistry will play a role, but one has to understand that chemistry alone cannot change the entire spectrum. The chemistry with engineering, chemistry with physics, and other subjects can only help. I would not talk much about COVID-19, but I can tell you that COVID-19 will certainly change the way the future research will be done. Not only education. Education, of course, is going to become online, but there will be a lot of efforts of protection of environment and climate. The environment and climate are extremely important. So lots of technological innovation has to be brought in. More digitalization will come in, and technology-enabled tools will replace hands-on experiments in laboratories. And that would be a future need. And I think many of the IITs, ICERs, IISc, universities, they're all now wondering what will happen in future. But I think in future, I can see a lot of changes will take place. And that is what we are calling new normals. New normal, when there will be opportunities to have innovative solutions. As I said, climate and environment, there will be a lot of trust in research in virology and pharmaceuticals. I think that's inevitable thing that will happen. Smart materials is very important because today, as we are going into more and more digital thing, how do you make innovative smart materials so that the contacts are not there? So maybe in sensors, a lot of work will happen in sensors, for example. How do you communicate subjects online? Because without eye contact, how do you teach students? I think that is still a big problem. All of us are teaching in different way. Even I myself teach in iPad, where I write like a blackboard, but it becomes very, very difficult to teach. So how do you communicate without eye contact, direct eye contact? I think that's going to be a major challenge in communication of subjects. I'm sure there will be a lot of innovation in education will come. Teaching of laboratory courses will also become a very important part of the new normal. Many of these in teaching as well as in research are actually going to be integrated by computation. Today, you know that computers are playing a very important role. In fact, all of us who are connecting in through YouTube, through Teams, Zoom, Google Meet, all WebEx, all kinds of things, we all are connecting through a computer or maybe a mobile electronic device. But the computer itself is, of course, going to be very, very important. However, the fact that computers are important has been realized in science actually long back. And that is what I'm going to talk, that in terms of science, not just in education, role of computer is very important. But computer alone is not enough. That is the reason we call it not even computer science, we are calling it computational science. It essentially means science where prediction can be done by computing something in the computers. And for that you need, of course, theory. That is very, very important. And this theory is validate experiment. And then we do computation, and together we try to find a solution. I think that is very important, that in next generation solution will come through the combination of theory, experiment, and computation. In fact, a very important quotation I would like to quote 200 years back, which says the more progress physical sciences make, the more they tend to then enter the domain of mathematics, which is the kind of center to which they all converge. We may even judge the degree of perfection to which the science has arrived by the facility with which it is committed to calculation. So you can see almost 200 years back, there is a prediction that in physical sciences, computation is going to become very, very important. Mathematics is going to become very important. However, if you look at this particular quotation, which I'm now showing, and this is in the context of chemistry, and that's one of the problems that the chemistry suffered from, shows that every attempt to employ mathematical methods in the study of chemical questions must be considered profoundly irrational and contrary to the spirit of chemistry. If mathematical analysis should ever hold a prominent place in chemistry, which is an aberration, which is happily almost impossible, it would occasion a rapid and widespread degeneration of that science. So it says 2 years after that mathematics cannot have a role in chemistry. Mathematics, it is irrational. Attempts to employ mathematical methods is irrational. And I can tell you how wrong is this particular statement. Unfortunately, many chemists suffered from the same dogma long after this statement was made. And I think that has been one of the major problems of chemistry. But today, we know that is not true. The computational chemistry and even in biology is not the same thing applied to biology. It's not just the domain of physics, but it has gone into chemistry and biology. Using theory, computers, and very fast algorithms, we can now solve complex equations from theory. So it's very, very important that we can solve these complex equations. We can predict in computers structure and properties of molecules, predict reactions between molecules, dynamics of evolution. We can model new materials. In fact, I'm sure Dr. Pradeep is going to talk on new materials. Professor Pradeep is going to talk on new materials. And we can model materials by computer. I'm going to show a few examples. We do a lot of drug design. In fact, during the COVID time, already people are looking at computer simulation of the viruses and then trying to find a drug by simulation. In general biological activity. And that's very, very important to realize that the computational science is enabling many of these today. Along with the pure physics-based approaches, I have to also mention that the two very important tools, which are artificial intelligence and machine learning, they are coming in a big way to solve many of these problems. So that is basically when you have a very large number of data, you use artificial intelligence and machine learning tools to resolve many of these. Before I start my technical, how computational chemistry is helping, very small, I must tell you that the computational chemistry as today understood is much of it is derived from quantum chemistry. And of course, it's fallout to classical simulations and so on. But the theoretical chemistry actually started even before that. Jean-Louis started talking of octet. Octet was actually talked of language, but I must say Jean-Louis already told about it. And a very famous paper on the atom and the molecule in Journal of American Chemical Society, he talked about chemical bond by the 8 electrons around the atoms. So in fact, it did not actually worry about modern quantum chemistry. But then came modern quantum chemistry. Erwin Schrödinger, 1927, Hitler in London, the hydrogen atom. This may change a lot of things. And eventually, of course, at small length scale today, we know that quantum mechanics or approximate quantum mechanics are extremely appropriate. At a larger length scale, however, we need to have a more classical approach, like molecular mechanics, because it's too large. Quantum mechanics is extremely unreachable because of the large independence of the computer time. So one has to do a classical mechanics or molecular mechanics or a combination of what is called QM and MM method. Even larger scale, people are now looking at mesoscopic and coarse grain simulation. Basically, at this classical approach, people forget about electrons. They take atom as the fundamental particle and directly write atom-atom interaction. For the coarse graining, they actually look at a group of atoms. You call it a bead, and then write interactions between the two beads. So these are all called the multi-scale methods. The length scale, as they're changing, you change your methods, and very often they're called horses for the courses. So depending on the course, you actually put your horse. So it's very important to realize. However, the length scale change was realized by Niels Bohr long back when he talked of quantum classical transition. If you remember, Niels Bohr talked about the correspondence principle. In the limit h going to 0, quantum principles go over to the classicals. So as you go from atoms and molecules to the clusters and nano and the bulk, you go from quantum to more and more classical approach. So I think it's very important to realize. However, the big billion-dollar question, which is still bugging all the theoretical chemists, where does quantum mechanics end and where does classical mechanics begin? What is the limit of quantum mechanics? What is the length scale? It's very hard to say. Of course, the cricket ball is classical. Atoms and molecules is quantum. What happens in the middle? Is the nanomaterials that length scale, which is a transition from quantum to classical? And that's a very tough question to answer. And many of the multi-scale simulations, one tries to answer. I would like to show this slide. And again, I will try to go full length for this slide, where you have simulation methods for soft materials. So you actually look at various electronic structure materials, electronic structure methods for molecules, which are called ab initio or quantum mechanics. Then you have the molecular simulation, as I told you, classical simulation, where atom-atom interactions are taken. That's a protein, for example. If you go to mesoscopic simulation or coarse grain, that's a polymer, for example, where beads or groups of atoms are taken. And then, of course, finally, the engineering length scale, which is CFD, finite element, Brownian dynamics, and so on. So today, depending on the material, depending on the length, one can use different simulation box methods. That is what I mean by horses for the courses. So this is the length scale, and here also goes the time scale. So time is also very important. Of course, if you go to large time, even in small length scale, quantum dynamics becomes extremely important. So when I talk of time, it has to be dynamics. So I just go back to the slide. So I think this is a very important slide that I wanted to mention. However, there are people who are actually using mixed quantum mechanics with classical mechanics in a very complex environment. And those are basically called the QMMM. 2013, the Nobel Prize was given. So here is an example of a QMMM. I give an example where I have an active part of a very large biological system, let's say where the drug comes and interacts. So it's a drug and membrane interaction. That's the blue region where you use quantum mechanics because the interaction energies are extremely sensitive. So one requires good quantum mechanics to be applied. The long length scale here, you can use classical mechanics. But then you need an interface region. It is very hard to go from quantum to the classical region directly. So one has to go through an interface region and then go to the classical mechanics. So this is a large environment that is modeled by a classical force field. But then the interface region is very, very important. And I think there are a lot of thought how to put the atoms here, the link atoms here, so that the quantum mechanics to classical mechanics environment, there is no jar. So this is what actually was a very famous work and done by the three gentlemen, Warshel, Leavitt, Karplus, who got Nobel Prize in 2013. And actually people today are talking of quantum mechanics, molecular mechanics, and coarse graining, CG. So it's a very complex mesoscopic or multiple length scale simulation. What I'm going to talk about is basically on quantum mechanics of two kinds of quantum mechanics. One which will be ab initio, which is proper solution of the Schrodinger equation. Another which is actually using density functional theory. And I must say that there are two different things. Both of them are quantum, but in density functional theory, you don't solve the wave function. And that makes density functional theory easier to apply for large systems, where energy can be written in terms of electron density. So this is basically today a method of choice in materials. I'm going to give some examples of materials. Energy is then expressed in terms of three-dimensional electron density. So that is the easy. It doesn't matter how large is the system. My basic variables are just three-dimensional electron density. The major problem in DFT, tuning the exchange correlation functionals. You can mix with the Hartree-Fock exchange. Sometimes you mix this functional with the Hartree-Fock exchange to get better results, and they are called the Minnesota functional. one needs to worry about how to take dispersion. And then, of course, different types of basis sets, either atom center or periodic. If you have solid, periodic solid, then you don't use atom-centered basis set like Gaussian. You use actually periodic basis set. So this is called periodic DFT, and there's a lot of interest in such work. I must caution you that while we do density functional theory, there are a lot of problems in density functional theory. I'm sorry for the slide, which is slightly hazy. I don't know why this happened. Let me just see. Anyway, so I just wanted to tell that these are very simple enthalpy changes. And if you look at the methods of DFT, there sometimes these are experimental methods, 544, 543, 203, 208. But look at this one, 21, 34, and so on. So they are reasonably reliable, but not always. Whereas methods like coupled cluster are extremely reliable methods. So they are actually called the gold standard of quantum chemistry today. I mean, the same thing happens if you do geometry optimization. There are kind of reliability errors that the DFT has. However, today we know, depending on the systems like atoms, molecules, and cluster to solid, we have to use the method. There is no other option because using quantum chemistry for solids is not possible. So for atoms and molecules, of course, we use atom-centered Gaussian basis sets. And even clusters of atoms, we can use quantum chemistry. But we have also realized here that the electron correlation is very important. So one has to look at ab initio methods like second-order perturbation theory, coupled clusters, Gauss SCF, complete active space, self-consistent field, wherever applicable. For periodic solids, you can integrate these methods with the periodic basis sets. But very often, for solids, because of the complexity, you can't use wave function-based methods. As I talked about, you have to use what is called the density functional theory. The cluster chemistry is often the link from the atoms, molecules to the solid, and very often also gives you a link to the catalysis. I'll come to the design of catalysis, how complex it is here. Of course, with the quantum mechanics, we can do density and molecular dynamics. This is completely classical dynamics. You can also do ab initio, Carr-Parinello, MD. I'm not going to talk about it, but I think molecular dynamics and time scale has also become very important. Let me now very quickly tell what are the problems we are doing, because it's impossible in this lecture to cover everything that I'm doing. So I'm just going to put a couple of slides on the different types of problems that we are doing. So one of the problems that we are doing, is to develop theories. Is this slides can be seen in the full mode? Hello?
No, sir. Full mode is not coming.
Are you able to see now?
Yeah, we can see it. Yes. No.
Not full mode. But this is not coming. This is not coming. This is not coming?
No, this is not coming.
Okay. Yeah, I'm sorry about it. All right, I wanted you to see this slide slightly better. All right, so one of the things that we are doing is called the highly correlated electronic structure method. So this is very important. As I told you, electron correlation is extremely important for atoms and molecules. And this is where we coin a very important phrase that is called getting the right results for the right reasons. I think that's a very important phrase. You can get right results for the wrong reasons. I hope you understand. Because of error cancellation in the theory, there can be two errors which cancel. So for a wrong reason, you may get right result. But what is important is to get right results for the right reasons. Two major activities that we have taken up in recent years are development of relativistic coupled cluster theory for ionization, electron attachment, and various other properties. In fact, we have published several papers in the recent years. Some of the important things that we have looked at, observed, is, for example, we have identified a mercury hydride with a high dipole moment. Now, please remember why you are using relativistic, because all these atoms are heavy atoms, and you need to use relativistic effects. So mercury hydride is a molecule where you have called that it has a very high dipole moment. Radium fluoride, for example, another molecule which has a parity and time reversal violating interaction. Plasma screening effects on multiply charged aluminum ions. We are also looking very recently on electron nucleus scalar pseudoscalar interaction in lead fluoride. Very recent papers I'm showing. So this is one level of methods where we're able to calculate various accurate properties by relativistic coupled cluster theory. I must talk about coupled cluster in the next slide, that the coupled cluster is a very, very important theory which gives very accurate results for the molecules. In the same manner, we are using the coupled cluster methods for resonance and decay, and I will just show one problem in today's slides, because the coupled cluster has been primarily bound state method. And the difference between bound state methods and the resonant states are that the resonant wave functions are not a normalizable wave functions. So they are not square integrable functions, they cannot be normalized. Whereas bound state coupled cluster, you can use only when the functions are normalizable. So it has been a big challenge to use coupled cluster for resonance and decay. Moiseev showed that if you use in the Hamiltonian a complex potential, then you can actually make the wave function bound. It's an artificial Hamiltonian, but he has shown that the resonance problem can be handled by a complex electron affinity. The complex part comes because of the complex potential, where the real part of the electron affinity is the resonance energy, and the imaginary part is a decay. This is much like what we teach in master's students, that you have a free particle in quantum mechanics that is not normalizable. But as soon as you put that in a box, particle in a box, that becomes normalizable. So that was a basic idea of putting a complex potential. But in this case, it's a complex potential, and we can actually look at decay. So we have looked at electron molecule resonance, we have looked at OJ decay, we have looked at interatomic Coulombic decay. Again, I will just probably give one example from the resonance, but I must say that there are several different properties that I can actually handle through this method, which I'm calling CAP, complex absorbing potential based coupled cluster method. To talk a little bit, then of course, we are doing lots of interesting application of DFT on functional clusters and materials. I will actually show again a few examples from my work on gold clusters, silver clusters, aluminum clusters, metal chalcogenides, very recent papers, and so on. First coming to the first part, I will say that the coupled cluster is, of course, an extremely well-developed method. And 1966, the landmark paper on coupled cluster came in the quantum chemistry through Jiri Cizek in Journal of Chemical Physics. And then later on, the coupled cluster methods were numerically coded, and CCSD, coupled cluster singles, doubles, and with triples became the gold standard of quantum chemistry. However, it's an extremely computation intensive method. There are standard methods of coupled cluster which are developed on single reference, which are called the dynamic correlation, but you can also take up the static correlation through a multi-reference coupled cluster. So one can today look at various types of electronic correlation, short range, long range, static, and dynamic through the multi-configuration coupled cluster method, which has become extremely important. There are a lot of people who continue to work on coupled cluster. I must mention Cizek, Paldus, Bartlett, Lindgren, Kaldor, Mukherjee, Kunzelny, Nguyen. I mean, several people, I must say. It's very hard to mention, but it has been a very well-developed subject. And what I'm going to talk here is an example where I told you that I can use complex absorbing potential to the coupled cluster to study the resonance and decay. And so because of the addition of complex absorbing potential, you can actually use any bound state method. Like DFT, you can use configuration interaction. Of course, we choose to use coupled cluster because coupled cluster is the most accurate among all the bound state methods. So this we are calling it CAP, complex absorbing potential coupled cluster. I will choose one example of SO2 minus resonance. I'm sorry about the recent example. In its ground state, SO2 minus is bound. However, the collision at a higher energy produces excited states of SO2 anion, which show resonances, and then they dissociate. There's an experiment which is performed by Jana and Nandi, and they could identify two resonance states. These are extremely difficult because they are not only, this is not a ground state which is resonant. The ground state of SO2 is actually bound, but these are the excited states. So doublet A1 and a doublet B1. And the second one is actually an admixture of doublet A1 and doublet B1. In theory, it is very difficult to calculate the admixture states. So with help of my co-workers and my student Suhita, who may be here in the YouTube, and of course Irina Jana also, who has been my collaborator, we have been able to nail down these resonance states. at a different geometries. So you can see we had talked of the resonance position as at 3.84 eV, and the width was completely not detected experimentally. These are very close to the experimental results, but these were not detected experimentally, so we could only predict the width, lifetime. Width actually is a matter of lifetime. So these two particular excited states which I mentioned, we have been able to nail down. One is a very short width, and one is a relatively much larger width. Of course, you can also do the same states at the ground state geometry, but they are not relevant because the geometry also plays a very important role. So we actually took the geometry of those two particular states. We have done several calculations. We have done several calculations without cap for electron affinity, ionization potential, and it has been a lifetime of my work in the couple cluster, but I'm not going to cover. What I'm going to cover in the last part is something that is less technical, but oriented towards applications. So I would rather say those are computational chemistry. So one of the important things that we have been trying to do is to design a catalyst. And all of you know in chemistry, design of catalysis is extremely important. However, there are several things that we have to look at. So reaction, metal selection, pre-catalyst, oxidation state, co-catalyst, additive, substrate, reagent, solvent, so many things that you have to look at, that it's a plethora problem. If you want to have a calculation with changing each of these, you'll have enormous number of data. And then you have to find out what is the best data. And that is where I think after doing quantum chemistry, artificial intelligence and machine learning can be employed. A lot of people are now looking at that as a tool to develop catalyst. Very quickly, my own work was focused on metal clusters, which are basically gold and silver cluster. Again, I'm very happy that my next speaker, Professor Pradeep, has also worked a lot on gold and silver clusters. Actually, he has been synthesizing them. In fact, I'm very happy because many of the clusters that we have been working on, he has told me that he will be able to synthesize. And he has synthesized. In fact, gas phase, I would say many clusters have been synthesized. Clusters, of course, show very exciting properties, because if you change one atom, the property of the cluster changes. So one of the important things that we looked at is, for example, 8-atom gold. 8-atom gold is actually experimentally synthesized in gas phase, but this is fairly inert. But what is very interesting is that if you monodope this AU8 with a silicon, make it SiAU7, it becomes catalytically active. Similarly, if you have pristine gold cage, it's not so active, AU18, but it gets activated if you put metal inside the cage. And I'm going to show some example. The same thing happens for hydrogen atom chemisort. If you can prepare hydrogen atom chemisort, and I'm told that again people are able to synthesize this cluster on a gold or a silver cluster, they become catalytically active. So not just the pristine cluster. Similarly, one very interesting cluster that we have looked at is an aluminum cluster, but not raw aluminum cluster. Aluminum cluster put on a graphene which is doped with boron nitride. So this is a very interesting material which again can be synthesized today, BN doped graphene. It's a molecule, boron nitride. And if you put aluminum cluster, our results show that that can be a very good catalyst for bond activation, particularly for nitrogen, oxygen, carbon halide, etc. So it's a very important cluster. So I'm going to show very quickly some of the results because it's very difficult to look at all the results. So this is, for example, the pristine AU18 gold cage. So I have taken a CO oxidation as a model example on this gold cage cluster. So if you look at, this is a complete reaction pathway. It's extremely difficult to do, I can tell you. So this is CO oxygen and the AU18. This has been all done by relativistic DFT because it's a gold, so we have taken relativistic. So if you look at this, I go through an intermediate, go through a transition state, another intermediate, another transition state, and finally the product. So the barriers eventually become 0.71 EV and 0.45 EV. The two barriers for getting this product CO2, the AU18 comes out. Let's look at the next slide in which I have put, I have put metals inside the AU18 gold cage. So sodium, potassium, magnesium, and calcium. And now you can see how far these barriers have dropped down, which essentially means the oxidation reaction would go much faster. So you have potassium, you have sodium. Of course, sodium is very dangerous. You may not be able to put, but I think magnesium in AU18 may be more easy to put. Once again, this is not an experiment. This cluster, nobody has put magnesium. These are predictions by computer. And that is where computational chemistry is becoming very, very important. I can predict. So I'm looking at the experimentalists who will be able to synthesize these clusters and do the reaction, the functional reaction for CO oxidation reaction. Same thing with the calcium, potassium, sodium, of course, does very good. I take up another example, which is the hydrogen chemizorb cluster. I talked about the hydrogen chemizorb cluster. If you look at AU6 and AU8, they're actually more or less, they don't do much. With oxygen, there is no activation. Barrier is very high. Again, it's a CO oxidation reaction that I'm looking at. Barrier is very high. But as soon as you put hydrogen, the barriers become very low. The oxygen gets elongated. The binding energy increases. You can see these results. And the activation barrier in particular drops down. If you look at AU6H, it's almost barrier-less. Even this has dropped down to 0.36 AV. So our prediction is, if you can prepare such cluster, they will be extremely good for the CO oxidation reaction. Once again, CO oxidation reaction is just taken as a model. What actually can do any oxidation reaction is our own idea. At the end, I will talk of another very interesting problem, where I'm going to talk of only one or two materials. I didn't talk of aluminum cluster or boron nitride graphene, but I can tell you that cluster has very well for nitrogen activation and various carbon halide bond activation. As a last example in materials, computational material science, I want to give this example of hydrogen storage. As all of you know, hydrogen storage is an extremely important problem. Onboard hydrogen storage, because it's not very difficult to synthesize, but carry it to where hydrogen will be used is a big challenge. So people are looking at a solid state storage for a safety. So the couple of things that we looked at is a metal organic framework, MOF, and a lot of people are doing that. People are looking at also COF, ZIF, and several materials, and magnesium. The problem that we looked at is that both of them individually are very bad, because this is a physisorb system, so hydrogen would be hardly absorbed. This is a chemisorb system, so hydrogen would be absorbed so strongly that the dehydrogenation will become a very big issue. So one need a material which is between chemisorption and physisorption. So typically, not too strong, not too weak. In fact, many people have looked at what could be the interaction energy. Metal organic framework, all of you know, is 1 to 5 kilojoules per mole. Magnesium is 60 kilojoules per mole, very, very strongly bound. So people are looking at 15 to 30 kilojoules per mole as an alternative. So one can again look at a strategy of doping metal organic framework or doping magnesium to bring it in this range. It's a very good strategy. In fact, one of them we have tried with magnesium also with silicon and aluminum, but I can again predict one very important material that we have looked at is a MOF5 or iron MOF1, which is decorated by scandium. Scandium does an extremely good job of increasing the potential of the MOF to absorb more hydrogen. And that is because, in fact, people had also tried titania. It did not work very well because titania starts to bind among themselves. But scandium does not cluster among themselves. It actually directly binds to the MOF5, and that raises the potential of MOF5 to absorb hydrogen. So it's a very important work that I believe, this can become a potential room temperature hydrogen storage solution. In fact, our own call is that one can properly synthesize this. It can at least bind hydrogen to the extent of 4% gravimetry at room temperature. And that's a huge thing, because today we know that only at the liquid nitrogen temperature, the people are looking at 12%, 15%, but not at room temperature. Room temperature, even 4% is very difficult. Of course, there are lots of materials. I must look at boron, ammonia boron. People are looking at perovskites and several different types of materials to do hydrogen storage. But these are some of the little things that I have done. I have also looked at scandium decorated ZIF7. ZIF, of course, many of you know, is zeolitic imidazole framework. So that is also becoming very important. So let me quickly try to finish by saying that doping, of course, has been a very useful strategy in material science. In fact, we know that the group 3, group 5 semiconductors are actually done by doping from silicon with silicon doping. And doping has been a very important strategy in the material science. Theoreticians today are able to look at nanomaterials. In fact, a lot of experiments are done in nanomaterials, and Professor Pradeep may also speak on it. But theoreticians have also looked at nanomaterials, and from the time that Feynman, Schrödinger said in 1952 that you cannot play with an atom or a molecule, and look at 8 years after what Feynman says, there is a plenty of room at the bottom. In fact, the two seminal discoveries, if somebody asks me what is the major science behind nanomaterials, I would say the discovery of electron microscopy and discovery of fullerenes, which actually led to carbon nanotubes. A lot of people today are using computation to do carbon nanotubes. I would actually close my talk here, except to say one very important part that I am not covering at all in the computational chemistry, that is the informatics. So what we are looking at is a theory-based approach, physics-based approach, the computational chemistry which is based on physics. But using artificial intelligence and machine learning, as I told you, one can actually have an informatics-based approach. And these are the two phases of computational chemistry, theoretical chemistry as well as informatics. I think it's very important. I'm not talking about informatics. A lot of people are working on chemo as well as bioinformatics methods to generate several things. But they are not physics-based approach. That is very important to realize. But I think it will be unfair for me if I do not mention this in the part of computational chemistry today. QSAR, quantitative structure activity relation, is an empirical relation which is used in the pharma or drug design very often. I think with this I will probably close, but just wanted to tell that again the materials or the areas which are emerging are energy materials, novel pharma materials, hydrogen, CO2 activation. Synthetic biology is going to play a very important role in chemistry, where chemistry will be inspired by biology. And I think many of these computation is going to play a very important role. And that's the reason I'm making a title of computational chemistry from molecules to materials. Once again, this actually tells all the different areas of work that we have been doing. And I think I'm just trying to make it a little bit bigger if possible. Yeah, sorry. So many of the materials that we're looking at, but our major interest has been on electronic structure of molecules, structural spectrum, model confined system, descriptors to address reactivity. That is where local hard, local softness comes in. We are actually specializing in many body coupled cluster methods for molecular properties. Then we are looking at density functional theory. We are looking at various principles, maximum hardness, minimum softness, minimum magnetizability, and so on. And then, of course, lots of materials for catalysis, gold, silver. We had looked at beta zeolites in the early days, and so on. So I think it has been an extremely great fun doing computational chemistry. I wanted to give a lecture which is not on any specific topic, but trying to convey to you the spirit of computational chemistry and the reach of computational chemistry, where we can actually go to various topics from molecules to materials. Depending on the system, we actually call for a method. So today it is not that I've been using quantum chemistry, I've been using coupled cluster all the time. Where it is required, we have used DFT. Where it is required, we have used Gaussian basis sets. Where it is required, we have used periodic basis sets. So I think it's very important that we have been developing different phenomena at the molecular level, where high level quantum chemistry is used. At the same time, we're looking at many application problems. So that's the reason I titled my talk as a computational chemistry from molecules to materials. Let me thank all my colleagues and collaborators and students who have been there with me for a very long time. And of course, many funding agencies like SCRB, DST, Indo-European Union, CSIR, Indo-French Center, Board of Research in Nuclear Science, DST DOD, and If I missed anything, I apologize. But there are many, many organizations which are given funding. Thank you very much for your interest, and I'm a little bit sorry for the fact that I could not go to the full slideshow model. Thank you very much.
Thank you, sir. Okay, so now, so from our Department of Chemistry of IIT Guwahati and Chemical Research Society Northeast Chapter, on behalf of other two organizers, Professor Pradeep Phukon and Madam from Tezpur University and Guwahati University, I thank you for your time, for sharing your experience with us. And we hope that soon we will be, once again, we'll be able to call you back for our departmental conferences.
Thank you. Thank you, all of you,
Thank you, sir.
Pradeep, Parameshwar, and all the
Thank you, sir.
IIT Guwahati.
Yeah.
Thank you, Nasreen. Thank you. Yeah.
Thank you, sir. Thank you.
Good to see you.
Thank you very much.
Thank you, Pradeep.
Thank you, sir.
The stage is
Yeah,
yours.
thank you.
So,
Thank you.
sir,
Thank you.
Very
so there
nice,
is,
sir.
there is Professor Pradeep and Professor Phukon also. Okay.
Yeah, of course. I talked to Professor Pradeep, T. Pradeep, for his talk. Yeah, of course, I also say hi to Pradeep Phukon, who is a very good friend of mine for a long time. Okay, thank you.
Thank you, sir.
Okay, sir. Thank you, sir.
Thank you very much.
Okay. So as a again, so welcome you all again once again, and all the YouTube viewer. Now as a part of the Chemistry Week, National Chemistry Week celebration by Chemical Research Society of India, on behalf of CRSI North Chapter and Department of Chemistry IIT Guwahati, along with Guwahati University and Tezpur University. And now, as a second lecture series, we are in the second day, second talk. So in this talk, please welcome Professor T. Pradeep from Indian Institute of Technology, Madras. He is the Institute Chair Professor. It's my pleasure to introduce him. So he basically works on molecular and nanoscale material. He is worked on some water environment related issues and instrumentants. So he has a visiting assignment in various places. So like Purdue University, Pohang University, South Korea, then University of Leiden, Netherlands, EPFL Lausanne, and Institute of Molecular Science, Osaka, Japan, and University of Haigo, Japan. So, and he has a huge list of award and honor. So that's why in his website there is a short list, there is a full list. So I could get some of them, because, and then is the Swarna Jayanti Fellowships, BM Birla Prize, Santishwara Bhatnagar Award, and JC Bose National Fellowship. So if you name any fellowship in India, he is having, and already more of that, he is as a highest civilian award Padma Shri in 2020 this year. So, and with this, I welcome Professor Pradeep to deliver his talk. Good afternoon, sir.
Well, indeed, good afternoon. Let me share my screen and see whether I am audible. Am I audible?
Yes, sir. You are audible. And we.
Okay. Maybe you are not seeing this slide.
We could see a PDF file, sir.
Yeah, I know. I'm just trying to make sure that the right file is seen. Okay. All right now?
Yes, sir.
I'm audible as well, right?
Yes. Yeah.
Fantastic. What a pleasure to be here on this particular occasion, just after Saurav Pal, and thank you, Gopal Das, for that nice introduction. Parameshwar Nair asked me to give this lecture, and it's also a pleasure to see you all virtually and be there at IIT Guwahati and Tezpur University and all the institutions were organizing. I chose to talk about give a flavor to you about this subject matter just after Professor Sauropal's lecture. I wanted to tell you that new materials are coming, and there is a whole lot of excitement about such materials. On the screen, you see many things. I will not be talking about any of those activities of science getting into industry and such other things. This lecture is truly on a very fundamental aspect of material science. For a very long time, we have been looking at matter. I mean chemists, physicists have been looking at matter. And this matter, for a long time, has been in matter with infinite atoms arranged. The connectivity between these atoms is such that they extend over infinite distances. And you call that as periodic solids. Well, with or without periodicity, you call them as solids. And soon, people started looking at matter with smaller pieces of constituent particles. So if you take a gram of some solid, you could make smaller pieces of matter and make that 1 gram of solid. And people started reducing that dimension smaller and smaller. Even at a few hundred nanometers, you have thousands of atoms within a particle. So let's say 3 nanometer gold particle, you have close to about 1,000 atoms in that. So that many chemical bonds. So people have made all of these for a long time. So what you see on the screen are a variety of nanoparticles that people have made. Now, they all have fantastic properties. We will not get into all of these. Around this time, when people started making all of these pieces of matter in all their variety, people also asked this question, as to is it possible to make matter at extremely smaller sizes? They call those matter, that kind of matter, as clusters. Although the name clusters itself is very old, is as old as Boyle, Robert Boyle, who introduced this concept or idea of clusters. But then that was, at that time, it was assembly of entities. In our common language itself, we have words, we use words such as clusters. In this lecture, we are talking about something else. So before getting into that, I should tell you that individual particles that you see on the screen, whether they are, let us say, some nanostars as you have, or nanorods as you have, people have explored them with very many tools. As Sauropal said, an important tool has been electron microscopy. But of late, people have also explored these materials with microscopy, optical microscopy in great detail. For example, this is one of our students' work. So these are individual silver particles of varying sizes seen by dark field microscopy. And this particle, for example, you can measure an optical absorption or scattering spectrum from that, or this particle you can collect that, or this particle you can collect that. You can, of course, do spectroscopy, essentially meaning properties of individual particles. This we can do very well in great detail. So today we measure Raman spectrum from an individual particle. Of course, you can go ahead and study the conductivity, electrical conductivity of an individual particle. So likewise, you could go to the extent that you could study catalysis at a single particle specificity. All of these people do in great detail. So when such kind of matter is explored in great detail, you ask this question, can you have atomic precision in such matter? This is to say that here in these particles, we don't have atomic precision. You could have 3,000 atom particle or 3,001 or 2 or 10 or whatever particle. And all of them will essentially show properties similar to what you are seeing here, the scattering spectrum or whatever else. But can you have atomically precise particles? This question itself has been very old. In fact, it is as something like today, this question is about 20-25 years old. Now, it is not to say that atomically precise clusters were observed only 20 years ago. No, people have seen them even earlier, largely with mass spectrometry, as Saurav Paul talked about. Here we are talking about atomically precise pieces of matter as chemical entities with precise synthetic methods, precise structure, precise properties. So here is one example of that. What would be better than a good mass spectrum for such a particle? This is a 25-atom gold molecule today, we say, or particle, protected with ligand. It is thiol ligand. The thiol that is used is ethyl, well, you would say phenyl ethyl thiol. So it is, people in American literature, you write phenyl ethane thiol. And this entity is SHCH2CH2C6H5. There are 18 of these. Protecting this entity, the H is gone off when you make this particular cluster. And it has a charge which is minus, 1 minus. And this is soluble in an organic medium. And today we have a mass spectrometric technique, an extremely soft ionization technique, electrospray ionization. So if you do electrospray ionization reasonably well, this particular one is nano ESI, you get a spectrum length. And you note that there is nothing here, which means that this ionization is super soft. It doesn't impart energy into the ion to cause fragmentation. Let me go back and show you this spectrum once again. And this is a high resolution mass spectrum. And you see that 7390.5718 is the major feature that you see. So there are several other features. All these features are due to the isotopic resolution in this cluster system. And that is a crystal structure of this entity. I will come to that in a minute. So here is that expansion of this particular mass peak, 7390.5718. And there are other peaks. You wonder, what is this, this mass spectrum in a gold cluster? Gold has only one isotope, 197. But gold also has sulfur. Along with gold, we have sulfur, which has 4 isotopes, 32, 33, 34, and 36. It has carbon. There are 2 isotopes of carbon 12 and 13. Hydrogen has 2 isotopes existing in nature, 1 and 2, hydrogen and deuterium. So So you put all that in a statistical distribution. This is what you see. Of course, there are many other peaks as well, but they are below the detection limit. So this is what you see. Now, high resolution, I said. So this mass spectrum has a resolution of 50,000. M by delta M is 50,000. So there are better mass spectrometers and better mass spectral data are available today. So here is one atomically precise cluster. Now this is about a noble metal, gold. So there are many other noble metals. There are many other metals. There are metal oxides. There are metal sulfides. There are metal chalcogenides. All of them can give you also clusters. But by and large today, gold and silver clusters have been studied in great detail. So my lecture today will have that, but we'll work on several other clusters as well. But time is short and therefore it is difficult to cover all of these. Now I told you that this question has been there for quite some time as to what can you make such smaller pieces, atomically precise pieces. What does that mean? It means you can write a molecular formula, atomic precision. Is it only molecular formula? No. If you say atomic precision, you have chemical bond precision. So that means you have a structure. When you have a formula, you have a structure, you have well-defined properties, of course. Now, you start exploring these properties, you see chemical properties and physical properties and spectroscopic properties and many others come into light. And I will show you largely chemical properties of the system to tell you that there is a new kind of matter beginning to gain interest. So that interest was there quite some time. So here is a paper. This is somewhere in around 1996 or so. So you see, it's already 24 years ago, 26 years ago, that people started looking at these. Now, this particular thing is a mass spectrum of gold clusters, protected gold clusters with in this particular case, it was laser desorption mass spectrometry. And they showed that upon laser desorption, all of these ligands go away, and what you have is essentially gold, pieces of gold. And the objective was to see where would you see cubic gold. Now, as Saurav was talking about, several such gas phase clusters have also been there. The most interesting of these is gold 20. Incidentally, this structure was proposed with spectroscopy and several other things, and subsequently this cluster was synthesized and its crystal structure was false, and it turned out to be the same. Just like C60, the structure was suggested and subsequently it was crystallized, etc. The kind of data that you see, this is called the photoelectron spectrum of negative ions. And this is to say that electronic structure was studied of such clusters along with their mass spectra for a long time. I will not have time to discuss this in detail. So having got these well-defined clusters in mass spectrum, obviously you can crystallize them. So here is something that you get routinely in the laboratory. So you take gold salt, you have certain thiols or phosphines or the kind of ligands that you may use today. We have acetylene. We also have even amine. So all of these are used to mix with this gold salt, and a reducing agent is added under appropriate conditions. You create clusters. Sometimes you, of course, make several other clusters, not only one cluster, and you apply purification, just like organic chemistry, and you separate these on liquid chromatography and get several clusters, you characterize them, purify them, put them into the NMR, apart from mass spec and several other tools. So when you study this, I hope I am audible. Am I?
Yes, sir.
So yes, good. Thank you. So when you have such clusters, you can put them into the diffractometer, and you can get a structure. So this structure is a reduced structure of gold 25 ligand 18 with the ligand being FCH3. So earlier I said phenyl ethane thiol. I can throw away the rest of the entity and I make this as just methyl, just for computational simplicity. Now, once you have this, of course, you have electronic structure of this. You can compute all the properties of this. These are gold atoms, and these are sulfur atoms, this is carbon and hydrogen. So as you can see, this is built with an icosahedral core with a center atom and 12 atoms outside, and then there are certain staple atoms. We'll come back to this a little later. So when you look at gold 25, this is what it is. But if I expand, well, if I take these sizes or metallic gold sizes, you will get an entity such as this. So this is a piece of, it could be considered as a piece of gold. Or you have an equivalent entity made of silver. So it is silver 25 ligand 18. But then there are several others as well, silver 29 and several others exist. Today we have over 150 different gold silver cluster systems existing. Now, this is not the only system that we have. What happens now? Am I on? My slides are seen, I suppose. Yes. So we have silver clusters as well. Other silver clusters as well. So one such silver cluster is silver 44. So this is the first such silver cluster wherein the central icosahedron atom is missing. So this is a hollow cage cluster, similar to fullerene, one may say. It has certain different, more number of atoms, and I'll come back to that. This has a different kind of ligand. Now, I told you about two ligands. These are certain different type of ligands, and the earlier one was phenyl ethane thiol, but then there are a large number of other ligands that people have used. I'll show you certain examples of very interesting new science that we are doing. Such clusters, because they are quantum confined, meaning electrons are confined in this kind of small sizes, they have distinct electronic structure different from bulk gold. Now, if I were to calculate the electronic energy levels, most of the frontier orbitals are derived from gold and sulfur, as you would imagine. Now, there are also electronic transitions between those levels. And if I were to irradiate a solution of that gold 25, well, this is not gold 25, a similar kind of a cluster, you will get an ultraviolet, if you irradiate ultraviolet light, you get an emission like this. So this is in the near infrared regime, about 650 to about 850 nanometers. So somewhere this is red in color. And today, these clusters are studied for a number of their optical properties because of their intense, high quantum yield. I wouldn't say really intense in comparison to organic molecules. So when you have molecules of this kind, we were interested in asking this question, can I have a chemical reaction between two clusters? So here is a cluster, here is another cluster. Is it possible to write a chemical reaction between them? No, obviously, this question is central to the nanoparticles. If nanoparticles are molecules or clusters are molecules, they should show molecular reactivity similar to molecules. So the moment I say that there is chemical reaction, I am also implying that there are chemical bonds which move in a particular fashion, so you have chemical reaction mechanisms. The moment I say that there are chemical reaction mechanisms, there are energetics associated with it, one would have kinetics associated with that. So what do you see? So at that point in time, I did not have that electrospray mass spectrometer to study this in great detail. We were studying this with matrix-assisted laser desorption ionization. In MALDI, when you put this gold 25 protected with another thiol, now this is fluorothiophene, I have a peak which is Au25 FTP18, that is this peak. Now, I also have another peak, Au21 FTP14. This is because Au4 SR4 is lost from this peak. That is because of a photofragmentation process that happens in laser desorption, upon laser desorption ionization in MALDI. This is not there in electrospray. If I were to take this cluster and mix it with this cluster, then, of course, this has another peak. I'm not showing you that mass range in which this peak is shown, but I'm showing you the mass peak in which this peak is shown. Here is a peak, and I am getting a fragment. Of course, in addition to that, just after mixing, I get a few peaks. I get another set of peaks here. So what is this peak? This peak is Au25 minus 1 Ag1 FTP18. This is 2, this is 3, this is 4, etc. So I have Au25 minus X, Ag, X, FTP18 is the general formula for this. Correspondingly, you have some fragments. So what you have is a gold 25 in which silver has been substituted. As a result, these peaks go down. Of course, if I were to look at this particular mass range, I would see that one gold has been inserted into it. Ag20, let us say 44 minus X, AUX, FTP30 would be a peak that is appearing on the higher side of the mass spectrum. With increasing time, this peak comes down in intensity and more of these peaks come up. And in increasing time, this peak disappears completely and an envelope of peaks appear. So what it tells you is that you can do molecular reactions. Keeping the structure constant, you can change one atom. Well, it is not just change one atom, a series of atoms. But then obviously, chemists have this question. Here is gold 25, here is silver 44, and I have not shown the alkyl or aryl groups here. Just for simplicity, gold and sulfur alone and silver and sulfur alone. Now you ask this question, if I were to take one silver and put it into this and one gold and put it into this, where will this gold go or silver go? As far as this particular structure is concerned, there is an icosahedral core and there is an icosahedral position which I call I, or the icosahedral surface. And then there is the staple position which I call S. There are 3 types of positions here, and there are 4 types of positions. Here an icosahedral position, there is no core as I told you before, and there is a dodecahedral vertex position or a dodecahedral facial position or a staple position. So I can ask this question computationally, which of these sites will be preferred? So if I take gold 25 and add silver into it, as you know, gold is more noble than silver. So any position, if I put a gold into this, silver into gold 25, no position is favored, whether it is central position or icosahedral position or a staple position, all of them are positive. Whereas if I were to take silver 44 and put one gold into it, which is more noble, all positions are favored, but one position is more favored. If I were to do a chemical reaction such that I change the central position of this gold 25 with Ag And correspondingly, I change the icosahedral or dodecahedral vertex or dodecahedral spatial or staple position of 44, I get this kind of energetic. So change here, correspondingly change here, I get a negative energy, but this energy is positive. But if you look at this in great detail, you see that this I for I substitution is more favored than other positions. So there is a thermodynamic advantage. In this particular case, I'm only showing you the enthalpic advantage. There is of course, there are entropic reasons as well. We will come back to this in a minute. So all of these are essentially driving this chemistry. So now you ask this question, a very interesting question. Ag44 is one in which 12 atoms are at the center. Now, is it possible that I can do a substitution chemistry of the kind that I just mentioned so that only this 12 atom at the center can be changed? And this is kind of organic chemistry that you do, or inorganic chemistry with specificity. So you do this specificity, and in fact, this particular set of data is suggesting that initially all of these positions, 1, 2, 3, 4, 5, 6, up to 12 atoms can be substituted. But later on, what happens is that here you have the 12, after some time, only one particular position remains. Is one, the kind of system that you get at the end is 12 atoms of this particular Ag44 have been substituted with gold. And which are these 12 atoms? These 12 atoms, it so turned out with spectroscopic studies and all that, is the central 12 atoms. So you can do in this particular structure with all the 44 atoms silver, selectively the 12 atoms alone can be modified by chemistry that we just mentioned. So there are several other interesting examples. We ask this question, how about this reaction? Au25 with Ag25, and because time is short, I will not get more into the details, but if you mix these two together, I get two peaks, Ag25 and Au25. And Au25, I label it as 025 to indicate that there is no silver in it, and G25, I label it as 25, 0 to indicate that there is no gold in it. But you mix it together, suddenly this peak comes up, this peak comes up, and I told you the reason for all that. This is a substitution. But then there are several other substitutions happen, which I'm not seeing here, but if I expand, I get all of these. And these peaks suggest that this substitution is more favored than other substitutions. This is the entropic reason. This has more greater entropy. And therefore, that is happening. Now, you ask this question, how would this reaction occur? This is a negatively charged entity. This is a negatively charged entity. Both of them are 1 minus charged species. If they come together, there should be a dimer. And that dimer should be 2 minus charge. And in fact, we can detect that dimer 2 minus charge right here if I expand here in the first initial 1 minute of this reaction. Now, this peak is the one that results in all these other peaks, and we can today compute all this dimer, and we can see that these interatomic distances are such that they are interacting, and atoms indeed exchange. Chemists, of course, can do many more interesting things. We can start with Ag25 and add a little bit of Au25 to it. And I told you before that an equilibrium distribution occurs. All these gold atoms essentially end up getting substituted. Now, this is favored, as I told you. Now, if you increase a little more of gold, you can increase its distribution, and one atom substitution can take this system all the way to this side. Meaning, one atom substitutions can happen for all the atoms in a given structure. So in order to understand which atom moves and which atom gets substituted, etc., you, in this particular structure, just as organic chemists do, if you have to write such a structure in great detail, you have to have a nomenclature. It is not only enough to say a structure as AU2 AG23, which is M25 structure. There are many distinct positions. Which of those positions are substituted? Which of those chemical bonds are broken? So in order to do that, we have to have a nomenclature. I do not have time to tell you, but a structure such as these can be constructed. Well, a nomenclature can be constructed to something like this. This structure is this structure. This is to say that there is a center atom. Around this, there is an icosahedral structure. And let us say these two atoms which constitute the icosahedron, there is a staple around it, and that is this staple. And there are these two atoms. Around this, there is another staple. This is that staple. This is this gold ring that you see. Correspondingly, nearly perpendicular, you have a green ring. You also have a blue ring, which essentially makes this structure. And each one of these atomic positions can be substituted. In fact, this particular structure is very similar to something called Borromean ring, and this is what it is. The Borromean ring structure implies that one chemical bond is enough to detach or dismantle this whole thing. This chemical bond will break this entire thing away. And that is the reason why chemical reactions occur with extreme, speed in this case. And this nomenclature I just mentioned to you is called aspicule nomenclature, which we introduce. Aspis means shield. Cules, of course, comes from molecules. So the name for a gold 25 is substitution. This is 2-phenylethyl thiolato. There are 2 of them, and 16 of methyl thiolato, gold 25. If specific locations are substituted with this, specific others are substituted with this, you have a nomenclature like this. You can simplify this nomenclature, and you can put a charge, etc. You can extend this this nomenclature can be drawn on the board to say that which of these atoms are breaking, which of these atoms are coming in, or which of these chemical bonds are broken, etc. You can extend this structure or this kind of nomenclature to much larger gold. This is gold 102, which is a structure. This is chiral. So you can also bring in chirality into this nomenclature. Now, this earlier argument that I just told you that clusters come together and make new chemical bonds, this can be seen in mass spectrometers. So you can see cluster dimers in the mass spectrum. Now, Gopal Das, how many minutes I have? I'm almost done, or another 5 minutes, or what?
Okay, sir. You have some time. 5 minutes?
Okay.
Yeah.
All right. So you have these cluster dimers, and you have many others that can be formed. In fact, if I were to take gold 25 and put it into a mass spectrometer, I can produce dimers. So here is a monomer of gold 25. Here is a dimer of gold 25, but this is 1 minus charge, this is 2 minus charge. You can also have 3 minus, a trimer. And all of them occur at the same mass numbers. That is because the charge state, 1, 2, 3. But separation between peaks, this is 1, this is half, this is 0.33. So you can see all of these happening in the mass spectrometer. You can also see this in solution probably. Now this also implies that clusters can come together and form new clusters. These are alloys. We make these as well. So subject area evolves. That is a cluster reaction is a subject area that evolves. I'll show you 1 or 2 more examples and close this lecture. So if I were to take this cluster solution and then ask this question, that clusters are of course reacting with 44 and 25 are reacting. Now, is it not possible that this gold 25 that is present here, of course, in the course of its motion or its life in this bottle, of course, it is encountering other gold 25 species. Will they not exchange atoms? Oh, that is a very complex question that you are asking. So if I were to say that a piece of gold, another piece of gold, if I put them together, will atoms go from one to the other? Well, this is not very much feasible in bulk, but can it be feasible at the nanoscale? So this is called cluster dynamics. But in the case of gold, it is very difficult to study because gold does not have another isotope. But this is possible in the case of silver. And if I were to show that these things exist, then I'm saying that they are indeed molecules, very similar to water. H2O and D2O, if I mix together, what do I get? I get HDO. That is because of the fast isotopic exchange when molecules interact with each other. So we showed that such isotopic exchange occurs in nanoparticles. So here is an example. In this example, the experiment that we have done is with silver 25. That experiment involved making 107 Ag25. So silver has two isotopes, 107 and 109, nearly equal in intensity, somewhere around 49 and 50. So this is 107. You can buy 107 silver from Aldrich Metal, and you can convert into silver nitrate, and then you can make this particular cluster. And this has a mass peak, and that mass peak is 5142. And this is a particular kind of ligand, dimethyl benzene thiol. The same ligand, 109 now, the mass peak is 5192, the separation is 5142, and 5192, the separation is 50 mass units. That's because the 25 silver atoms. Now, I have this compound and this compound pure, and in the mass spectrum, I can measure these separately, and I mix these two together. And I mix these two together, suddenly only this peak comes up. This is an isotopically mixed 25 and 25. This peak is completely absent, and this peak is completely absent. And in fact, it happens at such a fast time scale that the first spectrum is 15 seconds. This is what you have. In 20 seconds and 25 and 30 seconds, it is completely gone. So this is a rapid isotopic exchange that happens in nanoparticles. Obviously, it has a kinetics. To study that kinetics, that particular system was not very good because it was fast. So we chose another cluster system where the kinetics is slower. It occurs in 500 minutes. And you see, when you look at this particular kinetics, you have three regimes, and it is a tri-exponential decay that you see. And each one of these rate constants essentially tell you that two different dynamics is happening. The first atom exchange on the surface, and then atoms that are exchanged on the surface, of course, move within this cluster system, then lead to an equilibrium. Now, of course, there are many other reactions that you can do. It's not just A and B cluster. A cluster need not be just a silver cluster. It can be an alloy cluster. So here is such a cluster. And then this alloy cluster can react with another cluster. So instead of a binary alloy, you can have a ternary alloy cluster. And you can go further and further, and I'm showing you here a cluster which is a ternary alloy, PDAUAG alloy. I told you about two types of clusters, AU and AG or PT or rhodium or whatever. Huh? But you can also have two different silver. And here are two different silvers coming together, interacting and forming completely different new clusters. And it has a mechanism, and two different new clusters occur. So that's also very interesting. You know, clusters, of course, are one category of materials, but there are nanoparticles. Can they react? These are nanoparticles, traditional nanoparticles, polydispersed nanoparticles, but they react with clusters and become extremely monodispersed nanoparticles. So very fast reaction. cluster reactions are not only molecular reactions of the kind between two clusters, there can be supramolecular chemistry with C60, for example. And it is also possible that clusters can create this kind of supramolecular adducts which are showing isomers. So here is an example wherein we took cyclodextrin, and some of the ligands have they complex the cyclodextrin. So when you do that, you can create a large number of adducts, and some of these adducts can show isomers. And unfortunately, this computer is taking some time. So you have these kinds of clusters, and these clusters, let us say this is a cyclodextrin adduct of X, which is this particular cluster. Now, some of these, there are several kinds of adducts that you see. Some of them have isomers. The adduct 1 has no isomer. This is shown by ion mobility mass spectrometry, but this particular cluster has an isomer. This also has an isomer. This has an isomer. This has no isomer. This has no isomer. And that is because such clusters are almost like transition metal complexes, an octahedral complex like. The cyclodextrin, if it forms something like this, there is no isomer. Whereas this particular thing, it can have this or that isomer, cis or trans, or this particular one has isomers, this particular one has isomers, whereas 5 and 6 don't have isomers. Clusters can form assemblies, and I don't have that slide to show you, but take a nanoparticle, let's say gold nanorod, and decorate them with clusters. And we have made such single crystals with clusters assembled around the nanoparticle. Now they have properties of these luminescence and plasmonic properties combined together. Why are you making those things? Well, there are a lot of applications. Before telling you about applications, I mentioned to you about clusters with ligands, but there are ligands such as proteins or DNA. They also make clusters. Obviously, such things can go into biological systems. With luminescence, it is quite exciting. So there is cancer diagnostics and such other possibilities with the biological possibilities largely around luminescence. But these clusters are very tiny and they show catalysis in homogeneous systems, right? You don't have to put it as a heterogeneous catalyst as Saurav Paul talked about. These molecules, very similar to iridium or osmium or whatever kind of systems, they show catalysis. They, of course, absorb a lot of light and convert them and can transfer this energy to other systems. So you have light harvesting. And with all that, today we see that the subject area is expanding tremendously. So today we call this this kind of material belong to an expanding category of atomically precise solids. So this kind of atomically precise solids, of course, is one of the categories of these atomically precise solids. As I told you, there are other oxides and chalcogenides and many others, and that area is also expanding. And this work was done or is done or being done at IIT Madras with this fantastic colleague who heads this institution. We are in a position to do something reasonable in this place with of course, wilderness around, a great laboratory and resources around with fantastic people. Several of them are working in this cluster area. Thank you very much. This work was done with lots of funding from various funding agencies, largely Department of Science and Technology. I continue to have lots of collaboration across the world and many from India. And thank you, and I will be glad to take questions if you have.
Thank you, Professor Pradeep. This is Parmeshwar. Gopal, you want to say something? So sorry, I was a little late. I was in an ACS this meeting, so I came in around 4:05, 4:10.
Yeah, sure.
Yeah. So if there are any questions, I request to please put them to Professor Pradeep.
Hello.
Yes.
Yeah. Gopal, please go ahead.
Yeah. No, because I said I have a meeting in the department, so I will request Parameshwar Iyer to take care.
Sure. No
Yeah,
problem.
sure.
I'm here. Yeah. Professor Pradeep from Guwahati University is also here. You have some question?
Yes.
Okay.
Open.
So thank you very much, Professor Pradeep, for a nice presentation. It's excellent.
Yeah.
Of course, I don't need to tell, everybody says that. And one thing, whenever you talk about these metal clusters, say which one will be the best catalyst. So actually, what is the main driving force, like entropy or energy or confinement or surface area? Which one you feel that is the best way to describe the catalytic activity of a particular metal cluster? Like if it is 12 metal or 20 atom cluster, which one will be the best fit for a catalytic activity?
Very nice, important question. But let me say that even for a given cluster, say 25 or 12 or any such thing, these properties are also greatly influenced by the ligand.
Okay.
So if you have this particular cluster, let us say this is some cluster, gold 25 with, let us say this is phenylethyl thiol. Now, people have found this cluster to be very stable, but only with certain ligands and certain other ligands, this cluster is extremely unstable.
Okay.
Now, people have found, as far as this particular cluster is concerned, there are specific atoms.
Okay.
I mean, this is not the realistic ligand. The realistic ligand, if I were to put its structure, you will find that only a specific kind of atomic location is more accessible. So let me take this particular geometry to illustrate this point, that in this, if I were to take all of these are specific locations, these are ligand locations. 1, 3, and 5. Now, here, if I were to look at this particular location, this particular one position, and this particular one position will be more accessible than other positions for a given ligand. Now, as a result, the kind of catalysis that you do will be essentially centered around here, because this is where the site is of action, and people have shown this. Now, if that site is not accessible because of the ligand structure, obviously that catalysis is gone. So, what I'm trying to say, then you understand the point. That it is important for a given cluster. You need to combine this nuclearity of the cluster along with the ligand structure to plan what kind of catalysis is possible with that.
That one more thing, say for example, yes, I thank you very much. And say for example, you are definitely for many clusters we need to have some stabilizing agent, like say sulfur containing particularly compounds.
Yes.
So in such case, say if you have more kind of stabilizing agents, then obviously that stabilizing agents are going to block all the metal surfaces. So in such case, that metal surface will not be exposed to make the catalytic activity.
Yeah. So what is happening is that as the size is expanding further and further, say for example something like this. Now this is only 44. People have made up to 310 and something. Now that's the last few weeks ago there was something that was crystallized around that. So in such kind of sizes, what happens, as you can see here, these are atoms which are essentially available. Now, these kinds of locations, when you go to larger and larger sizes of clusters, you have many atoms Now, why are they exposed and why are they not bound with the ligand? It is because this inherent electronic stability of these metals themselves have reached such a level.
Okay.
So as far as smaller clusters are concerned, of course, most of all the surface atoms are bound, but larger clusters, many atoms are outside and they are available.
Yeah, yes, correct. Yeah. Thank you very much.
There is a request from a few students to share your slides. I hope you know.
You have anyway the recording, right? And this can be shared across.
Sure.
So
yes.
so that can be done.
Okay.
And then if anybody wants something specific, they can always ask me.
Yeah, sure.
Being a YouTube kind of a thing, you don't really.
We did not give you much time for deciding. It was a short invitation time. You still accepted it. Thank you so much. And it was really wonderful, and I'm sure the audience in this region would have really benefited. Hopefully things will normalize and we can also invite you here in the near future. Yeah,
absolutely.
Thank you. Yeah.
Thank you very much. Thank you.
Great.
Thank you so much. Yeah,
Thank you.
Thank you. Okay.